Welcome to an intriguing journey into the origins of our solar system. This course, part of the space science program, will delve into the fascinating processes that shaped the celestial neighborhood we call home. Our learning objectives include understanding the scientific importance of solar system formation, exploring early ideas about cosmic creation, and examining the modern nebular theory. We'll also uncover why rotating disks form during gravitational collapse. Why study solar system formation? Discover why planetary orbits are nearly circular, mostly in the same plane, and revolve in the same direction. These patterns suggest underlying physics rather than random placement. Let's explore the architecture of the solar system. Key observations include coplanar orbits, a common direction of revolution, and the distinction between inner rocky planets and outer giant planets. Early theories like the catastrophic hypothesis and close stellar encounter idea attempted to explain solar system formation. However, they faced problems such as angular momentum distribution, indicating a need for better explanations. The Kant-Laplace Nebular hypothesis, proposed in the 1700s, suggested that a cloud of gas and dust contracts under gravity, leading to a spinning, flattened, and hot disk. This was the first scientific theory of its kind. Transitioning from Kant-Laplace to modern nebular theory, astronomers and physicists refined the model over 2 centuries. Advances in observational technology, astrophysics, computer simulations, and cosmic chemistry confirmed the model. Solar systems begin in massive, cold gas and dust clouds. These clouds collapse and spin due to gravity, forming dense, hot regions known as protostars. Later triggers, like supernova shockwaves, further influence formation. As a nebula contracts, it spins faster, conserving angular momentum. This principle explains the formation of rotating disks and the direction of planetary orbits, highlighting the quantitative science behind cosmic structures. Gravity pulls matter toward the center of mass, while centrifugal force causes flattening. This balance of forces leads to a spinning, flattened disk, explaining why planetary orbits are in a plane. The collapse forms a hot circumstellar disk of gas and dust, where material clumps into planetesimals. The disk differentiates into hot inner and cooler outer regions, further explaining the planar nature of orbits. Telescopes like ALMA and Hubble observe protoplanetary disks around young stars, confirming the theorized planet formation process. Dusty disks are visible in infrared and radio wavelengths, indicating many solar systems are forming. Here's a timeline overview, from the collapse of giant molecular clouds to the emergence of the solar system. Each stage, from spinning nebula to planetesimal formation, plays a crucial role in cosmic evolution. Let's delve into conceptual questions. How does angular momentum explain disk formation? Why do protoplanetary disks flatten and differentiate? What evidence supports their existence? How does modern theory build on early ideas? In summary, modern nebular theory explains solar system origins through collapsing, spinning clouds of gas and dust. Disk formation leads to planets forming within the same plane, shaped by conservation of angular momentum and differentiation. Observations confirm the existence of protoplanetary disks, inviting us to explore the stars.